In this video, we're going to continue our discussion of interest-bearing accounts. So we talked a little bit about simple interest, but as you may know, many accounts don't grow based on simple interest. They actually grow based on interest that is compounded. So particularly accounts that are based on credit grow at a fast rate. This is because the interest is compounded. So what that means is essentially interest on your interest. So compound interest is computed on both the principal, in other words, the original amount in the account, the amount that we put in the account, or if it's a loan, the original amount we're taking out for the loan, as well as any previously accumulated interest. So in other words, if you've already been charged interest and it hasn't been paid off, then over the next cycle of interest, you're charged interest on your interest. In other words, your account balance is accruing a lot faster, and each time you calculate interest, the amount of interest actually changes. So interest that is compounded in general is going to be higher than simple interest as long as the interest rate is the same and it's the same period of time. Now, one of the biggest differences between simple interest and compound interest is the fact that with simple interest, the interest you add on each time is always going to be the same. So because it's only based on the principal, every time they add interest to your account, the principal didn't change, so they're only charging you interest on the original amount in the account, not any additional interest they've already charged you. With compound interest, essentially what's happening is your interest is then being reinvested in the account every single time it's charged to the account. And so each time they charge you interest, they're considering pre-existing interest now part of the principal. So they're charging you interest on your interest. The effect is that you have a different interest charge each time in general, since you're charging interest on an additional amount that's now part of your principal. So the most important takeaway is it grows faster, your interest payments increase over time in general, as long as the interest goes unpaid. Now, what we want to focus on is how we'd actually calculate interest that has been compounded. So the good news is, for the most part, we have the same variables. So the same variables that we had for simple interest, we still have. We're going to add on one additional variable, and we'll talk about what this means. So we're going to assume that we deposit P dollars, so P is our principal, at a rate R, which represents our interest rate. Here's where we have our additional variable. So it's going to be subject to compound interest that's paid in times per year. So this new variable N is going to represent how many times we charge interest per year. N is going to vary based on how we charge interest to the account. We'll talk about how we identify N in just a minute. So based on these values, the amount A, so A represents the account balance or the amount in the account, after T years, so T being time, and again, it's annual, so the same assumption we had with simple interest we have here, it's got to be annual in terms of years, is going to be given by the following formula. So it starts out pretty much the same as the simple interest formula, but once we get to the location where we have R, again representative of our interest rate, this is where things change. So our account balance is going to be P, our principal, times the quantity, 1 plus R divided by N, and now notice we have an exponent attached to this formula. The exponent explains why accounts that are accruing compounded interest gets big so much faster than accounts that have simple interest. Anything involving an exponent grows a lot faster than something that doesn't involve an exponent. So the exponent explains why the account is going to get bigger faster than it would with simple interest. Now let's break this down a little bit. So this R divided by N, what's going on here? Well, we know we have our interest rate R. N represents the number of times we accrue interest per year. So what's happening right here in the formula is we're actually taking the interest rate, which is applied across the whole year, and we're dividing it into parts based on how often we accrue interest. So essentially what's happening is, rather than applying the whole interest rate every single time we calculate interest, we're only applying part of it. So say for instance we calculate interest twice a year. Well, rather than applying the whole interest rate each time, we would actually take that interest rate and divide it into two parts. And each time we calculate interest, we're actually only applying half of the interest rate rather than the entire interest rate. So this particular term represents how we're applying interest, but it divides that interest rate into parts based on how frequently we're calculating interest. So rather than using the whole interest rate every single time, we're only using part of the interest rate, and equal part distributed over the course of the year. Now our exponent is going to be n times t. So t still represents time in years, and again, n represents how many times we calculate interest per year. So n times t actually represents the total number of interest payments. If you take the number of years and multiply by how many times per year you calculate interest, that's going to represent the total number of interest payments across the life of the account. So either across the savings account, whatever you want to think of it, or across the life of the loan until we have to pay back the loan. Okay, so we talked a little bit about the variable n. It's going to break our interest rate into pieces depending on how frequently interest is charged or paid out. So the length of time between two interest payments is what we call the compounding period. In other words, that's the length of time that elapses over which we accumulate interest until that interest is actually charged to the account. So determining the value of n is not as simple as just identifying a number in the problem. Usually the value of n is going to be identified by some adverb in the problem related to a time period. So these will be the kind of words you see that will tell you what your value for n is going to be. So if you're told that your interest is compounded annually, annually means once a year. So think about it like you have a birthday annually. You have a birthday once a year. So interest compounded annually is compounded once a year. So the value for n would be 1. If we calculate interest once a year, then that means the length of the compounding period is going to be 1 year. In other words, 1 year elapses from interest payment to interest payment. That's what that means in terms of the compounding period. Now, what if our interest is compounded semi-annually? The root semi actually means half. So that means take the year, take the annual period, and divide it into two parts. So in that case, n is going to be 2. We're dividing the year into two parts. So that means the length of each compounding period is going to be 6 months. In other words, if we're taking the whole year and we're dividing it into two parts, then we have 6-month intervals between which each interest payment is made. So the compounding period is going to be 6 months. What we're going to use in the formula, though, is going to be the value for n. So keep that in mind. This just tells us how long everything elapses between interest payments, but what we're actually going to use in the formula is going to be the value for n. Now, another option is that we might compound quarterly. Dividing something into quarters means dividing it into 4 parts. So that means our value for n is going to be 4. We're dividing our interest payments into 4 across the year. Well, if we're taking the whole year and dividing it into 4 parts, that means the compounding period is going to be every 3 months. So 3 months are going to elapse between interest payments. Now, we're going to see a lot of situations where we compound monthly. In other words, we calculate interest every single month. We have an interest charge every single month. You can probably think of some situations in your own life where you have interest payments that occur every single month. Think like a credit card. If we have monthly compounding, then our value for n is going to be 12. So we're dividing the year into 12 parts, which means each compounding period has 1 month in length. So month to month, we go 1 month between each interest charge, each interest payment. Now, if we're compounding weekly, there are 52 weeks in a year, so that's going to be 52. So each compounding period is 1 week. If we divide the year into 52 parts, then the length of each compounding period is 1 week. And then if we compound daily, which is certainly an option, n is either going to be 365 or it's going to be 360. So remember, we talked briefly about this issue in the last video. Financial institutions are technically allowed to take 365 and round it off to 360 just to make the calculations a little bit simpler. So when we're talking about compounding daily, it's either going to be 365 or it's going to be 360. Now, you have to be told which one you're going to use, so you will be told. You'll either be told that treat a year as 365 days or to treat it as 360 days. Regardless, at that point, we're dividing the year into that many pieces, and the compounding period is going to be 1 day in length. So just as compounded interest increases faster than simple interest, the more frequently we compound, the higher the interest is. So if you have the same account that has the same interest rate, it starts with the same principal, you're keeping it for the same length of time, the faster you compound, the more interest you'll expect to accrue in the account. So that's just something to keep in mind. So let's look at a few examples. Okay, so suppose you deposit $7,500 in a savings account that has an interest rate of 6%. The interest is compounded monthly. How much money will you have in the account in 5 years, and how much of that is interest? Okay, so how do we know we're looking at one type of problem versus another? In other words, if you're just given a financial problem, how do you know whether or not to use a simple interest formula or to use a compound interest formula? You're looking for this key word, the word compounded. If that word is there, compounded, compound, compounding, some type of version of that word, that means we're looking at a situation where we're going to use the compound interest formula, which is going to be the one that has the exponent. If you don't see the word compound, compounded, compounding, something like that, if you don't see that anywhere in the problem description, that means we're using simple interest. So you may not be told outright that it is going to be simple interest, but you will have to be told outright that it is compound interest, because you'll have to be told how the interest is going to compound, how it's going to accrue. If you're not told that, if you don't have that particular word or that particular phrase in your problem, automatically that means you're looking at a simple interest problem. So just keep that in mind if you're looking at a financial problem out of context and you're not sure which formula to apply. That's going to give you information about which formula to apply. So we know we need all the same variables as with simple interest, with the addition of this one variable n. So we need to also determine the value for n since we're looking at a compound interest problem. Okay, so let's go from the start. So we're depositing $7,500. In other words, that's where the account balance is going to be starting. So that's going to be our principal. That's going to be the value for P. Now our account has an interest rate of 6%. So that's going to be the value for R. Now remember, we can't just directly plug 6% into the problem. We're going to have to convert that to a decimal. So we're going to use 0.06 in place of 6%. Now we're told that the interest is compounded monthly. So that means every single month we're charged interest. Well, how many parts would that divide the year into? Well, if we're dividing it into monthly parts, that means we're dividing the year into 12 parts. So that particular word right there, combined with the term compounded, tells us that our value for n is going to be 12. So compounding monthly means 12 times a year, so n is going to be 12. Now the question is, how much are we going to have in the account in 5 years? So 5 is going to be our value for T. Now since the question is how much are we going to have in the account, we are looking for the account balance. So that means A is going to be our variable. That's what we're trying to identify. But notice there's a second question. There's also the question, how much of this is interest? So in other words, if we look at the entire account balance, what portion was attributed to principal and what portion was attributed to interest? We also want to answer that question. Now, we'll start with the first question. So how much money will we have in the account in 5 years? So we identified all the variables. Now we just need to plug it into the formula. So let's look back at the formula real quick. Okay, so we have our principal times 1 plus our interest rate divided by n. So remember, in this case, n is going to be 12 since we have monthly interest. And we have an exponent of n times t. Okay. So we have our account balance is equal to 7,500 times 1 plus our interest rate, which was 6% or 0.06, divided into 12 parts because we're compounding monthly. And then we have an exponent of n times t. So again, n is going to be 12, and then t is going to be 5. So now we just need to simplify all of this down. Now, as with simple interest, you can type it all in one line, or you can go one operation at a time. I want to show you how to do it both ways. So let's just start by typing it all in one line. Okay. As long as you're careful and you use your parentheses strategically based on how they're written down, you should be fine typing it all in. Now, one word of advice, the exponent, just because there's a couple things going on in the exponent, my recommendation is that you go ahead and simplify the exponent, determine what that actual simplified number is going to be before you start typing anything into your calculator. That way you don't have to type extra operations inside of the exponent. So go ahead and simplify the exponent and then just type the simplified version into your calculator. We know 12 times 5 is going to be 60, so rather than typing 12 times 5, I'm just going to type 60 when I get to the exponent. Okay, so I have 7,500, then we have parentheses, we have 1 plus r over n. Now either you can write r divided by n, or if you've got this particular calculator, remember it's got a fraction button, so I'm going to use the fraction button. So we have 0.06 and then tab over, and we have a denominator of 12. Now make sure when you close your parentheses that you tab back over and you're out of that denominator before you type your closing parentheses. Now we need that exponent of 60. So your exponent button is going to be on the left-hand side of your calculator. It's going to be an up arrow. If you have a different calculator, you'll have a button that looks similar to this, but it may be in a slightly different location. So you're looking for the up arrow. So I type the up arrow, it formats an exponent for me, and then I'm going to type in my exponent of 60. And there we go. That's going to be our account balance. So $10,116, and if we're talking about cents, then that's going to round to 38 cents. Now you'll notice I have a different answer here. Why do I have a different answer? Well, this would be an answer that you would get if you were to round step to step. Ideally, we want to avoid rounding as much as possible until we get to the very end. This would be the closest to the exact answer. This particular answer means we didn't do any rounding in the calculator. We just typed it all in, and this would be the final answer just based on no rounding, just based on plugging things into the calculator and keeping that running total. So this particular answer would be preferable. The least amount of rounding you can do, the better, because it's going to be closer to the exact answer. Now, what if I didn't want to type it all in one line? What if I wanted to go step by step? What are the benefits of doing that? Well, again, as we mentioned last video, the benefits of going step by step mean that you can write down your work as you go. If you type it all in one line and maybe you mistype something in your formula, how do you show that in your work? I mean, how do you show your work? How do you get partial credit if there's no work written down and all there is a right answer? How do you get partial credit for something like that? Well, the answer is you probably don't. So it's important to have a strategy to be able to show your work, even if you're doing a problem that very heavily relies on using a calculator. So by going one operation at a time, you then have things you can write down that allow you to show your work. So let me show you what that looks like here. So keep this in the back of your mind. This is our exact answer. We can get to this in a different way, just doing one operation at a time. So I'm going to clear this. Okay. If I wanted to type this in, but I only want to type in one operation at a time, I have to go based on, I was about to say Pythagorean theorem, not Pythagorean theorem. I have to go based on order of operations, PEMDAS, that's what I was looking for. So what do we need to do if we're going to follow order of operations? Well, order of operations says start inside parentheses. So we have to start with the operations in parentheses. Well, in this case, we have two of them. We have an addition, and that fraction represents a division. Then order of operations tells us we'd have to do the division first. So the first thing I have to do if I'm going to do one operation at a time is I have to do that division. So 0.06 divided by 12, and there we go, so 0.05. Well, what would come next? Well, I've done the division, now I have to do the addition. So to that value, I'm adding 1. That's now going to be what's in parentheses. So that gives me a chance to write something down and show my work and show what I have as subtotals leading up to our final answer. So that's going to be 1.005, and that means we've simplified everything in parentheses. Well, what comes next? Well, again, in theory, you want to go ahead and simplify the exponent at the very beginning so that you don't have an operation inside of the exponent. We know that exponent is going to be 60. So at that point, we still have the number out front that's being multiplied, and then we also have an exponent that's going to be applied to everything in parentheses. So multiplication and then an exponent. Well, clearly order of operations tells us that the exponent would have to come before the multiplication. So rather than taking 7,500 and multiplying it by 1.005, which is very tempting, we'll talk about that in a minute, we have to do the exponent first. So based on the value we now have, we're going to raise that to the 60th power. So up arrow and then 60. And then I'm going to hit enter. This will be the point in the problem once you apply the exponent where suddenly you run into numbers that it's possible you would have to round. So this would be a point where if I wanted to write something down in order to show my work, something would more than likely have to be rounded. So notice at that point I rounded off to 4 decimal places. So rather than 885 and then continuing, I have 89, and that's where I stopped. If I were to then work off of this rounded version, that's how I might end up with a slightly different answer than the one I actually had in my calculator, just typing it all in one line. So rounding in the middle of the problem may have a trickle-down effect so that your final answer is slightly different. However, if you just keep working off of what's in your calculator, you don't have to worry about rounding until the very end because your calculator isn't rounding. It's just adding on one operation at a time. So we've applied the exponent. Last thing we have to do is then multiply by the amount of principal, which is going to be 7,500. So times 7,500. And that's going to be our final answer. And if I'm not mistaken, that's what we had typing it all in one line as well. Okay, now I want to talk about this issue with the multiplication out front. Let's go all the way back to the beginning. What is tempting to do here that we cannot do? Well, if I see that 7,500 and then I see something in parentheses and I notice that addition, one thing that immediately jumps to my mind is the distributive property. It looks like something where we might distribute that 7,500. We cannot do that in this situation. Why can we not do that even though it looks like we should? It looks like the kind of setup where you would do that. The reason we can't do that is because of the exponent. We have to go back to order of operations. So distribution means multiplying into parentheses, and then the exponent, of course, just means taking an exponent. Order of operations tells us that an exponent would always have to be applied before a multiplication is applied. So by distributing that 7,500, which again, it looks like you could or should do, you're violating the rules for order of operations. You're taking the multiplication before you apply the exponent. So what that means is this 7,500 cannot be distributed. Ultimately, if you're going to go step by step and do one operation at a time, multiplying by that 7,500 should always be the very final thing you do. Every single problem where you use the compound interest formula to find an account balance, the very last step is going to be the multiplication by the value for the principal out front. You're not going to do it anywhere in the middle of the problem. It's always going to be the very last step. What you'll find is that if you try to distribute it or if you try to multiply it at this point, your final answer is going to be a really, really big number. What do I mean by that? Well, suppose you multiplied right there. You said, okay, it's going to be multiplied because I have those parentheses. So I'd have 7,500 times 1.005. Okay, pretty big number. And then we have to apply the exponent, right? So raise that to the 60th power. 60th power, there we go. Overflow error. Notice your calculator can't even handle that number. So does that mean there's no answer? Well, no. It means you took a really big number and then multiplied it by itself 60 times. That is not what's happening here. What's happening is we're taking this value in parentheses, which represents how our interest is growing, and then we're raising that to the 60th power. Only once we've applied the exponent can we then multiply by the principal. So just keep that in the back of your mind. It looks like a situation where you have a number, you have parentheses, you multiply them together. You don't do that multiplication until the very end. Now that's not going to be an issue at all if you just type it all in one line, but if you don't plan on doing that, if you want to be able to show your work at least a little bit as you go, keep that in mind. That multiplication out front will always be the final thing you do. Now we have one more question. The question was, based on our account balance, how much of that represents interest? Now we're in a slightly different situation than we were with simple interest. If you remember, when we talked about simple interest, we actually had two formulas. We had a formula for calculating an account balance, and then we also had a formula for just calculating the amount of interest. We had a formula with A, we had a formula with I. Unfortunately, it's not going to work that way when we're talking about compound interest. Why not? Well, as I mentioned at the beginning of the video, one thing that differentiates simple interest and compound interest is the fact that with simple interest, the amount of interest accrued every single time, every single year, is always going to be the same. It's a fixed amount, and that fixed amount is just added into the account year by year across the life of the account. When we're talking about compound interest, the amount of compound interest added to the account changes over time. Because remember, we're applying the interest rate not only to what was originally in the account, our principal, but we're also applying it to any interest we already accrued. So the amount we're applying that interest rate to every time changes. So the amount of interest changes every time. All of that to say there is no straightforward formula that allows you to directly calculate interest if your interest is compounded. You can calculate your account balance, but if you want to calculate the amount of interest, you have to work backwards. So interest is just defined as whatever else is added to the account above and beyond your principal. So think of this as the check that you would have to write to repay back a loan. Or in this case, we have a savings account. This is where our savings account started, and this is the value we had in the account after 5 years. We're making the assumption that this was all that we put into the account. We only put $7,500 in, and then we just let it sit there. We didn't take anything out, we didn't add anything in. So what accounts for the difference between the $7,500 and then the $10,000? Well, the difference between the two was the interest we accrued. So if we want to know how much interest we accrued, it's always going to be the difference between the two. So our account balance minus what we started with, $7,500, that's going to be the amount of interest. But notice we worked backwards to find it. We didn't directly calculate interest, but we just used the fact that interest is always the difference between where our account was and then where it ends up. The difference between the two is always the interest. So that's going to be how we calculate the interest if we want to know what the interest is in a compounding situation. Let's look at another example. So we looked at a savings account. Now what about a loan? So we take out a $4,000 loan that charges interest at a rate of 12%. The interest is compounded quarterly. If you don't make any periodic payments and simply pay back the entire amount at the very end, how much will you owe after 10 years and how much of that is interest? Okay, same idea. We want to know entire amount at the very end. How much are we going to have to pay back? In other words, what will the account balance be after 10 years? So 10 is going to be our value for T. We're taking out a $4,000 loan. So $4,000 is going to be our principal. Our interest rate is going to be 12%. So that's going to be P, that's going to be R, that's going to be T. Now we have one additional value, in this case N. I see that word compounded. So that tells me we're going to use the formula that has an exponent and also requires the value for N. Well, we've been told that we're compounding quarterly. So every quarter, every 3 months. Well, how many pieces does that divide the year into if we're compounding quarterly? Well, quarterly means we're dividing it into 4 pieces. So that means our value for N in this case is going to be 4 based on compounding quarterly. So I'm going to plug everything I know into my formula. So my principal is going to be $4,000. 12% interest, we changed that to 0.12. And because we're compounding quarterly, we're dividing that annual rate into 4 parts. Every time we accrue interest, we're only accruing 1/4 of the interest rate's worth of interest. And then our exponent is going to be N, which is 4, times T, which is 10. So let's just type this all in one line to save ourselves a little bit of time. Again, if you were going to go one operation at a time, go ahead and simplify your exponent first, but you're going to do the division, the addition, which gives you everything in parentheses, and then your exponent, and then the very last step is always multiply by the principal out front. So let's all do that in one line and let's see what we get. So we have 4,000 times the quantity, 1 plus 0.12 divided by 4. So notice in this case I typed it as a division rather than a fraction. It means the same thing. Fractions, division, same thing. Close our parentheses, and then we're raising it to the 4 times 10 power, in other words, the 40th power. So raising it to the 40th power, and then we hit enter. So that's going to be our account balance, $13,048.15. And if we round to the nearest dollar, that's going to be $13,048. Now, keep in mind, if you're doing that intermediate rounding, then potentially you may end up with an exact answer at the end that doesn't have any cents attached to it. But this is going to be the exact answer in the sense that there was no rounding done. Everything was just built on by the calculator, and this would be the point at the problem where you could round. Okay, now we also want to know how much interest is in the account. So based on that being the account balance, or that being the account balance, how much interest was applied to the account? Well, interest is always defined as the difference between where the account starts and where the account ends. So if I take the balance in the account and subtract how much of that balance is attributed directly to the loan, to the principal, in other words, $4,000, then the difference between the two is going to be the amount of interest. So in this case, notice that based on how that relates to the principal, if the principal was $4,000, this is more than double the amount of principal. If we doubled the principal, that would be $8,000. We added on more than $8,000. So the interest was far and away the majority of that balance in the account. That's the way compound interest works. In a lot of cases, the effective interest is stronger than the effect of the principal. In other words, we have more money based on that balance that we can contribute, that we can attribute to interest, than we actually attribute to the value of the loan or the original value of the account. Okay, let's look at one more. I think this is kind of a cool example. In 1626, Dutch settlers purchased the island of Manhattan from the local indigenous tribe for the equivalent of $24. In other words, in 1626, Manhattan was supposedly worth $24. Suppose the value of Manhattan increased at a rate of 5% per year. How much will Manhattan be worth in 2026? In other words, 400 years later, assuming two different conditions. Assuming we calculated simple interest, in other words, the value increased based on simple interest, and interest compounded annually. In other words, we want to compare the effects. This is going to allow us to compare the effects of simple interest versus interest that's compounded. Okay, so a lot of things are going to be the same here. The only thing that's going to change from one situation to the other, besides the formula, is going to be the addition of that one variable in as related to compound interest. But principal, rate, amount of time, those are going to be consistent from situation to situation. So what is our principal in this case? Well, our principal is going to be $24. That's the original value of Manhattan, supposedly. So that's going to be P in both situations. What we want to know is, how does P grow based on different interest-bearing conditions? So P is going to be $24. Now we're increasing at a rate of 5% per year. So that's going to be our value for R. And then our question is, how much will Manhattan be worth 400 years later in the year 2026? Okay, so we know our value for P, we know our value for R, we know our value for T. Now in the situation where we're compounding, the second option, we're compounding annually, which means only one time a year. That would be like calculating interest on January 1st, and then the next January 1st you calculate interest again, but you don't have any interest payments in the middle. If that's the case, then that means our value for N is going to be 1. Now let's start with the simple interest. So remember, that's going to be A is equal to P times the quantity 1 plus RT. So our principal value is 24, 1 is just 1. Our interest rate is 5%, so 0.05. And then our amount of time is going to be 400 years. So we're multiplying that by 400. Now again, we can do this step by step, which would mean multiply and then add and then multiply by the 24 out front. Or alternatively, we can just type that in one line. So 24 times 1 plus 0.05 times 400, close your parentheses, and that's going to be the value. What does that mean? Well, that means $504. So if we only increased value based on simple interest, then Manhattan goes from being worth $24 to being worth $504. So think about that. Does that mean that's a realistic model for how the value of Manhattan would grow? Well, more than likely it's not. In that case, it's not realistic. Is Manhattan worth $504? It might be worth a little bit more than that. So more than likely, the simple interest model is not going to be an effective model for showing how value changes over time. Now, what about interest that's compounded? So remember, P, R, and T, those are going to be the same. We're compounding annually, which means N is going to be 1. So we have 24 times 1 plus R over N, so 0.05 divided by 1, raised to the N times T power, so 1 times 400. So in this case, notice our exponent is going to be 400. So if we want to type this in, let's just go step by step for this one. I want to show you something that happens. So if we go step by step, one operation at a time, we're going to do the division first. So 0.05 divided by 1. Okay, we're adding on 1 to that, so plus 1. Okay, now we're raising that to the 400th power. So raised to the 400th power. Look at that. We went from 1.05 to, let's see, 3 digits. That's 299 million. Why do you think compounding is going to make more sense in this situation? Well, it's going to make more sense because of what the exponent does. The exponent takes a small number and then increases it so that it's a really large number. Why is that? Well, remember what an exponent means. An exponent means repeated multiplication. So what's really happening when we take this number and raise it to the 400th power is we're taking 1.05 and we're multiplying it by itself over and over and over and over again. Each time we multiply by itself, that's demonstrating the effect of how interest accrues from year to year. It's showing how the interest increases from one year to the next. And so after 400 years, this is the ultimate effect in terms of how interest increases that original balance of $24. So if we then take that number and multiply it by 24, that's going to be the actual value we have. So again, if you're not sure what your place in value is, count from the right. So 3 places, 3 places, 3 places. So that's going to be 7,176,000,000. That's going to be the value of Manhattan based on compounding, but compounding annually. Now, I would argue that that value is probably still too low, but if you compare the two, that very clearly shows the difference between what simple interest does to an account and what compounding does to an account. If you wonder why people stay in debt for such a long time, it's because interest is compounded. Anything that goes unpaid then accrues interest. And ultimately, this is an extreme situation, but the idea is the same. If you collect interest on your interest, look how big things get and look how fast they get big. Okay, now let's switch gears a little bit. So we've calculated account balances. We know how to calculate the amount of interest. We can also use the compounding formula to determine how much money is needed today to meet a financial goal in the future. So suppose you want to have a particular account balance. You want to have a certain amount of money available to you. You might also ask the question, well, if I have this kind of account that has this interest rate and I have this length of time to just allow my money to sit there, how much money do I need to put in to meet this goal of getting to this particular account balance? We can also use the compound interest formula in that way. So from a practical standpoint, what does that actually mean? Well, what it means is we're going to have the value for A. We're going to have a particular account value that we want to reach. But if we want to know how much money to put in today to meet that goal, then what we're looking for is P. In this case, P, our principal, is going to be our unknown. But we can solve for P in pretty much the same way that we solved for P when we were looking at simple interest. So let's look at an example. So a woman wants to celebrate the birth of her first child by setting up a college fund for him. The available investment pays 6% interest compounded semi-annually. So I see that word compounded. Automatically, that means I'm going to use the formula that has an exponent in it. How much should the woman deposit on the day her child is born so that the account balance will accumulate to $40,000 on the day he turns 18? Okay, so let's go through and let's look at what we know. Well, we see our interest rate, so 6% interest, and it's compounded semi-annually. So semi-annually means we're dividing the year into two parts. That means our value for n is going to be 2. The question is, how much should we deposit today, the day the child is born? That means we're looking for P. That means P is our unknown. So that we have $40,000 18 years later. So T is going to be 18. We have 18 years between the day the kid is born and then the day we want to have our goal met. And the goal is to get to $40,000. That's the account balance we want to reach. So that's going to be the value for A. So we know A, we know our interest rate, we know the amount of time, we know how this particular account compounds interest. The only thing we don't know is what we need to have in that account to start with in order to meet that goal in the future. So let's plug in what we know. So A is going to be 40,000. P we're going to leave as P because again that's our unknown. 1 plus our interest rate of 6%, so 0.06, compounded semi-annually, so divided into two parts. And then our exponent is going to be n times t, so 2 times 18 years, so t is going to be 18. Now how do I approach this? Well, because my variable is in the middle of the problem, it's not already isolated, the goal ultimately is to isolate it and then simplify everything on the other side of the equation. What I want you to notice though is everything else besides P on the right-hand side of the equation is just constant. It's fixed numbers. So we have an addition, we have a division, we have an exponent, but all of that would just simplify down to a single number, right? It would be a single number that's then multiplied by P. And if you remember when we simplified to find A, we took all of that and started by simplifying all of that. And then we multiplied by P. So what this means for this kind of problem is that if we can simplify all of that on the right-hand side of the equation, then it's just a number multiplied by P. Well, if we want to isolate P and it has something multiplied by it, then we just divide it and move it over. So in this kind of problem, what we want to do is simplify that, and then we use our simplified value in order to isolate P. So I need to know what all of that on the right-hand side is going to simplify to. So I'm going to do that, and I'm going to do that in the calculator. Again, you can do it in one step, or you can simplify a little bit at a time and then just build on it. If we do it in one step, we have 1 plus the fraction 0.06 divided by 2, close the parentheses, and then our exponent is going to be 2 times 18, which simplifies to 36. So we're raising this to the 36th power. So that's going to be the number that is then multiplied by P. Okay, now we talked a little bit about this next issue when we talked about simple interest. The goal is to now take that value and move it over to the left-hand side, thereby isolating P, our variable, which is the goal. Now, we cannot just hit divide and then type 40,000 because that represents taking this number and dividing it by 40,000. That's not actually what we want to do. What we want to do is divide by this number, divide by that number in the calculator. So what we really want is 40,000 divided by this number. So this divided by 40,000 and then 40,000 divided by this, not the same thing. Division order matters. So how do we get around that issue? Well, we want 40,000, so 40,000, and we want to divide. What we want to divide by is that number. Do we have to retype it? Well, fortunately, the answer is no. We don't have to retype that. What we're going to do is we're going to use that copy function in the calculator. So I'm going to go down to the very bottom. Notice right above the negative button, it says A and S, which stands for the answer from the previous line. But it's in green, which means I can only get to it by using the second button first. So I'm going to hit second and negative, and it's going to copy that answer, the exact answer, not a rounded version, but the exact answer, into the next line. And then I have the division I want. I have 40,000 divided by this particular factor that I wanted to move over in order to isolate P. And so I do that division, and that's going to give me what I want. Now again, notice this particular answer, this is based on rounding. So if I rounded that number that I then divided by, the final answer also has a little bit of a rounding issue. Whereas if I build off of it in the calculator, this is going to be the exact value, or as close to the exact value as we can get based on our limited means. So this would be the preferable answer because it doesn't involve any rounding until the very end. But that's going to be our balance. That's going to be what we need to have as a balance to start with in order to get to $40,000 in the future. Now, just a word of advice to help you make sure that your answer makes sense. If we're talking about meeting a goal in the future, it makes sense that we'd start with something that's smaller. The idea is you're putting a certain amount in the bank now, and then you're using the fact that your account accrues interest in order to get from this balance to the balance you want in the future. So if you were to work a problem like this where you're trying to determine what the principal is and you end up with a number that's larger than 40,000, it doesn't make any sense. Because again, the goal is to start with a certain amount of your own money and then build on it based on the fact that you have an interest-bearing account. So automatically the principal should be less than what the account balance is. If it's not, then more than likely it means maybe you misassigned a variable, you did something like that. Maybe you didn't convert your interest rate correctly, something like that. But in that case, you need to go back and you need to check your work, and you need to make sure that everything matches up the way it's supposed to. Now you could also take your answer and plug it back in and simplify the right-hand side of this equation and make sure it roughly comes out to 40,000. That's another good way to check and make sure your answer makes sense. So if you type all of that in and it comes out to close to 40,000, then that means your answer makes sense. If it doesn't, then again, it means you need to go back and check your work. Maybe you just need to type it into your calculator again. Okay, let's look at another one. A 30-year-old worker plans to retire at age 65. He believes that $500,000 is needed to retire comfortably. How much should be deposited now at 7% compounded monthly to meet the $500,000 retirement goal? Okay, so the goal is to get to $500,000 in the future. So $500,000 is going to be our account balance. The question is how much should be deposited now to meet that goal. So again, we're solving for P. We're looking for our amount for principal. Well, we have a 7% interest rate account, so that's going to be R, and it's compounded monthly, in other words, 12 times a year. So N is going to be 12, and that term compounded means we're going to use the formula that has an exponent attached to it. Now, what about time? Time is given here, but it's given kind of implicitly. So this person is 30 years old now, and he wants to retire at 65. So that means he has 35 years over which to accumulate interest and to meet his goal. So that means our value for T is going to be 35 in this case. So A is going to be 500,000. It's equal to P, which is our unknown, times 1 plus our interest rate divided by 12. And then our exponent is going to be 12 times 35. So this is the same setup as the previous kind of problem. Notice P is our variable. We want to isolate P, but P is now multiplied by everything that could then be simplified and divided out and moved over, which would then isolate our P and give us the answer we want. So we need to start by simplifying all of that P is then multiplied by. Now definitely you want to simplify the exponent first. So 12 times 35, that's going to be an exponent of 420. So when it gets to the point to type in our exponent, that's what we're going to type. Okay, so we have 1 plus 0.07 divided by 12. And then we're raising that to the 420th power. Okay, so that is now the number multiplied by P, and you can see it below, the rounded version. What are we doing with that number? Well, we have to divide it out in order to isolate p. This is the number that's multiplied by p. If we want to get rid of it, we have to divide it and move it over. But remember, we're not taking this and dividing 500,000. It's the other way around. We're taking both sides and we're dividing by this number. So I need to take 500,000 and then I'm dividing by that number. So divide by the answer from the previous line. So second and negative brings up the answer from the previous line. And then I hit enter. So $43,455.01. That's going to be what we need. That's going to be the principal we need today in order to accrue interest and get to $500,000 over 35 years. Now, just a word of advice in terms of entering your answers in when you're trying to type in answers like this. Pay very close attention to the rounding instructions. It may specifically say round up. Why would it specifically say round up? Well, if you think about this particular rounded answer, which is the correct rounded version of this number, technically that is rounding down in the sense that the actual values we need based on the whole decimal expansion, it cuts off some of that. So this number is technically smaller than the actual number in the calculator. What that means realistically is if we were to use this as our starting point, then over 35 years, it's going to get close to 500,000, but it may be right under 500,000. So in order to meet a goal, we potentially have to round up, even when the normal rounding rules don't say to round up, just so we make sure we meet the goal. What it means is that we'll slightly pass the goal, but if we're under the goal, then we haven't met it. Whereas if we're over it, then we have met it. So pay very close attention to your rounding instructions. It may say round up to the nearest dollar, round up to the nearest cent, something like that. If that's the case, say it said round up to the nearest cent. Well, that means 1 cent would round up to 2. Or if it said round up to the nearest dollar, then we would round to 43,456, not 55. So just be aware of that. That is a potential issue, and that's why. In order to actually meet a goal, we have to make sure we hit it and possibly pass it, rather than being slightly under it. Okay, let's look at one more thing, and then we will wrap this one up. So comparing investments. What if we have different options in terms of accounts that compound? How do we know which account is going to be better? Well, if we're looking at simple interest, say we want to make money, the goal is to make money. Well, whatever account you keep longer and has a higher interest rate is going to be the better account. Unfortunately, it's not that simple when we're talking about situations where we compound, because different things can change. What can change that might make a difference? Well, of course, the interest rate can change. A higher interest rate in general is better. But what can also change is the compounding method, how often interest is calculated. So ultimately the question could be, what if we have a higher interest rate, but we don't calculate interest as often, versus a lower interest rate and we calculate interest more often. So remember, in general, higher interest rates get you more interest, but calculating interest more frequently also gets you more interest. So what if it's balanced out in the sense that one account has more interest, but one account compounds more frequently? Well, how do you know which one's going to be the better investment? Unfortunately, there's no one-to-one comparison. You just have to calculate what the balance is going to be in either situation. But in general, once we do that, if the goal is to take out an investment, in other words, make money, you want the account that's going to pay the most interest. If the goal is to take out a loan and find the best deal, you want the account that's going to charge the least amount of interest. But there aren't going to be any shortcuts saying, lower interest rate is better for a loan, higher interest rate is better for an investment, because we also have to take into account what the compounding looks like. So let's look at a couple examples of this. Let's look at an investment first, and then we'll look at a loan. So suppose you have $6,000 to invest. Which investment yields the greater return over 3 years? 7% compounded monthly or 6.85% compounded daily? So what's the trade-off here? Well, the first option has a higher interest rate. The second one has a lower rate. But the second option, we compound more frequently. In other words, you get interest added to the account more frequently, whereas with the first one, you get interest added less frequently. So higher rate, but less frequent compounding, lower rate, more frequent compounding. What's going to be their better deal? Well, we have an investment, so the goal is to make interest. We want whichever account is going to make us more interest. So we just compare them. We need to know what's the balance going to be in either situation. What we're going to find, though, is only certain parts of the compounding formula actually affect the difference between one account versus the other. And I'll talk about that in a minute once we get through all of it. Now, what's going to be consistent from situation to situation? Well, we're investing the same amount of money no matter what, and we're keeping the account for the same length of time for 3 years. So principal is going to be $6,000, and then time is going to be 3. What's going to change is going to be the interest rate, and then our value for N, which represents how we compound. So in the first situation, we're investing $6,000. Our interest rate is 7%, and we're compounding monthly. So we're dividing that into 12 parts, and then our exponent is N times T, which is going to be 12 times 3, aka 36. So let's see what that balance is going to be. So we have 6,000. We're multiplying by 1 plus 0.07, divided into 12 parts, and then we're raising it to the 36 power. Oops, go back. There we go, 36. And that's going to be our account balance. So we grow from 6,000 to about 7,400. Okay, now we want to compare that to the other investment as well. So what if we decrease the interest rate, but we increase how frequently we compound? Is there a good enough difference in order to make that a more valuable account? So we're changing R, and we're also changing N. So now N is going to be 360. We're going to say daily means 360 in this case. And so our exponent is now going to be 360 times 3. Notice 3 didn't change because we're keeping the account for 3 years regardless. So 360 times 3 is going to be our exponent. So let's see what that's going to be. 360 times 3, 1,080. So when I type it in, that's going to be my exponent. So we have 6,000 times 1 plus the fraction 0.0685. Now we're dividing that into 360 parts. So we're dividing it so that each part of interest is smaller, but the exponent is what counteracts that. So close the parentheses, and we're raising it to the 1,080th power. And there we go. That's going to be our balance. So 73, 68, and 69 cents. So just based on comparing the two, the first option is actually going to give us a slightly higher account balance. And so if the goal is to make an investment and make money, the first option is going to be the best, all other things aside. Now, what I want you to notice is what had the effect on this. We had different interest rates, we had different compounding periods. In this case, the first combination was better. What I want you to notice, though, is the 6,000. It didn't actually have any effect on the situation. Why not? Well, it was consistent from part A to part B. All that 6,000 did is multiply by that particular factor that demonstrates how we increase interest. But because it was the same from situation to situation, it didn't actually have any impact on the final answer. What do I mean by that? Well, if we were to leave that out, it would not actually change the answer. We would still determine that the first option would result in more interest, and then the second option would result in less interest. So what if we were to just type in those other two parts and leave out the 6,000? We should get the same conclusion. I want to show you that we do. So we have 1 plus 0.07 divided by 12, close your parentheses, and we're raising that to the 36th power. So 1.2329, okay? This is the multiplier that applies to 6,000. It tells us how that original balance is going to increase. It's going to increase by this factor, which results in this final value. What we're really comparing from investment to investment is this multiplier, this particular value that then increases the $6,000 in a certain way. So what if we went with the other account? What is the multiplier for that one? Well, let's see. We have 1 plus 0.0685 divided by 360. Close your parentheses, and it was raised to the 1080 power. And there we go. Notice it's a slightly smaller number. They're pretty close. But once you take that and then multiply it by another number, the effect is substantially different. We actually have a difference of multiple dollars in that case. Imagine if you were investing $1 million. The effect would be even larger in this case. So ultimately, because the multiplier was higher for the first investment, that's what makes the determination about which investment is better. Not the actual principal, because that's consistent from situation to situation. It's the multiplier, which takes the interest rate, takes the compounding terms, puts that all together, and that's what makes the determination for us. Okay, let's look at another one. So that's if we want to make an investment. The goal is to make money. So we want whichever account is going to make us more money. Now, what if it's the other way around? So we need a $15,000 loan to purchase a car. You've narrowed your financing options down to 2 choices. So option A would be 10% that's compounded monthly, or option B would be 10.5%, but it's compounded semi-annually. All other considerations aside, which option should we choose? So lower interest rate but compounded more frequently, or higher interest rate but compounded less frequently. Which one's going to end up being better? Well, again, we can't just compare because it's not apples to apples, it's apples and oranges. But what we're determining is which multiplier is going to have the least effect. In this case, we want to take out a loan. So the idea is to have as little interest as possible. Which one is going to result in the lowest balance? Which one's going to result in the lowest amount of interest? Now, one thing I notice here is we don't have a period of time. If you look through the whole problem, there is no length of time. But time is kind of like the principal in the sense that that was consistent from situation to situation. For the first one, it was a length of 3 years, and that part was the same from situation to situation. So that particular part didn't actually have any effect on the final answer because it was the same from situation to situation. So ultimately, just like the principal, the amount of time doesn't actually have any effect on what the final answer is. So as long as you pick an amount of time, say just 1 year, it's not going to make a difference from situation to situation. It's not going to change your final answer. So I'm just going to pick a length of time of 1 year, and I'm going to keep it consistent from option A to option B so that we can then just analyze the difference that the interest rate and the compounding has on the situation. So we have a principal of $15,000, but what we really want to compare is those 2 multipliers. Which one's going to be higher, which one's going to be lower. So let's just compare those 2. So 1 plus 0.1, so 10% compounded monthly, so it's divided by 12. Oops, delete, close that. And then we're raising it to the n times t power, and we've decided we're going to let t be 1 year. You could let it be 2, you could let it be 3, as long as it's the same value for both options. In this case, 1 just keeps it simple. So that means we're only raising this to the 12th power, and that's going to be our multiplier. So 1.1047. Now what's going to happen with the next one where we increase the interest rate, but we don't calculate interest as often? We want to compare that multiplier as well. So 1 plus 0.105 divided by 2, so 10.5% interest compounded semi-annually. And then we're raising it to the 2 times 1 power. So close your parentheses. 2 times 1 is going to be 2. So we're then squaring it. And that gives us 1.1078. So if we're taking out a loan, remember the goal is to have less interest. Larger multiplier, more interest. Smaller multiplier, less interest. So in that case, the first option is going to be the better option because it's going to result in less paid overall. We still have to pay back the same principal, but for option 1, we'll have to pay back less interest overall. So that gives you a sense of some of the kinds of problems you might see involving compound interest. One thing I do want you to keep in mind, both with simple interest and compound interest, based on the kinds of problems we've looked at so far, the underlying assumption is that the principal is fixed. What does that mean? Well, it means that once we take out a loan, that's the amount of the loan. In other words, we're not making payments over time. We're thinking of it as just paying off the whole loan at the very end. Same thing with an investment. If we have a savings account, something like that, we're dumping a bunch of money in the bank on day one and then we're leaving it alone. We're not taking any money out. We're not adding any money to the account. That's not necessarily representative of what happens when you have an account or when you have a loan in real life. If we're making payments over time or we're adding to the account over time, we have to adjust these formulas in order to deal with that situation. So in the following videos, we're going to talk about how that looks. What happens if you make payments on your loan? What happens if you add in money to your account over time? Something like that. These particular situations handle the cases where it's one fixed value at the beginning and the only changes to the account represent changes specifically from interest.